All right, I want you to picture a specific object.
Okay.
It's it's likely something you've seen before, maybe sitting on a dusty shelf in a high school physics lab
Mm-hmm.
or, in a museum gift shop right next to the Newton's cradles. It's a clear glass bulb about the size of a light bulb.
Right. And inside, there's that little spindle with 4 veins on it.
Exactly. 4 veins. One side of each is painted a matte black, and the other side is shiny silver or white.
The Crookes radiometer.
That's the one. The light mill. You put it in the sun, and it spins. It spins really fast.
And it's been doing this since 1879.
And if you ask almost anyone, and I mean including my old physics teacher, why it spins, they'll give you a very, very confident answer. They'll say, oh, the light pushes it.
Or the black side gets hot.
Yeah.
Something like that.
And usually they're wrong. Or at least
Significantly incomplete. Yeah.
that is exactly why we're digging into this today. Because this Victorian-era toy is actually the center of a massive century-long argument in physics.
It really is.
We've got a stack of sources today.
Yeah.
But we're centering on a fascinating paper by Jerry Z. Liu that claims to finally solve the mystery. And the solution isn't, simple mechanics.
No, not at all. It's a new theory called transimpact, and it basically turns this little desk toy into a quantum mechanical engine.
It's an incredible detective story. You have some of the smartest people in history, Maxwell, Einstein, taking a crack at this thing, and the standard explanations just kept failing to match the data.
Exactly. So let's unpack it.
Okay, so before we get to the new theory, this transimpact, we have to understand why the old theories just crash and burn. Because I think a lot of us, myself included, still believe them.
Sure.
So let's start with the inventor, William Crookes. It's 1879. He builds this thing. What did he think was happening?
Well, Crookes was absolutely convinced he had built a device that demonstrated radiation pressure.
Okay,
He believed that light is made of particles, what we now call photons, and when those photons hit the vanes, they physically push them.
like throwing hail against a signpost. It sounds incredibly logical. Light has energy. Energy exerts force.
It is logical, and in fact, James Clerk Maxwell, the absolute titan of electromagnetism, he supported this view.
Wow.
He looked at Crookes' device and said, yes, this is light pressure in action. The math suggests light has momentum, so it should push.
So, case closed. Maxwell says it works. It works.
You would think so, but there's a huge fatal flaw in that logic, and it has to do with how momentum works when something reflects versus when it's absorbed.
Okay, walk me through this.
All right, imagine you're holding a heavy medicine ball. You throw it at a wall, and it just sticks there. Thud. The wall gets pushed back a certain amount, right? Now imagine you throw a super bouncy rubber ball at that same wall with the same force. It hits the wall and bounces right back at you.
Okay, I think I remember this from physics. For the ball to bounce back, the wall has to push it even harder to reverse its direction completely.
Exactly. A reflection transfers twice the momentum of an absorption.
Wow.
So apply that to the radiometer. The black side absorbs light, that's the medicine ball sticking. The white side reflects light, that's the rubber ball bouncing.
So if light pressure were the driving force,
The white side would be pushed twice as hard.
which means the radiometer would spin with the white side retreating.
The white side would be at the back of the car. Yes.
But if you look at any light mill in the world,
It spins the other way. The black side retreats. The black side is being pushed.
so Maxwell, one of the greatest physicists of all time, got the direction completely wrong for this specific device.
He did. It's an amazing miss.
Okay, so light pressure is out. It spins the wrong way.
Yeah.
That brings us to the explanation I was taught. Heat. The thermal creep theory.
Right.
The black side absorbs light, it gets hot, it heats the air nearby, and then the air pushes it. That seems to fix the direction problem.
It does fix the direction. The black side gets hotter, so presumably the air pushes against it more. This is actually where Einstein got involved with his edge effect calculations, but this theory has a different problem.
Right.
It's too slow.
Too slow.
Think about heating up a cast iron skillet. It doesn't happen instantly, right? It takes time for the metal to absorb the heat, for it to conduct to the surface, and then to transfer that heat to the air molecules. It's a whole process.
So if the heat theory were true, when I shine a flashlight on the radiometer, there should be a delay, a lag.
Exactly. It should start slow. The acceleration should, ramp up as the temperature rises and the air gets moving.
But that's not what happens.
Not at all. The data in Jerry Liu's paper highlights something really weird. When you turn on the light, the acceleration hits its maximum peak instantaneously
Instantaneously.
at time 0. The moment the photons hit, the force is applied. It doesn't act like a steam engine building up pressure. It acts like it's being kicked.
Okay, that definitely contradicts the idea of waiting for air to heat up. But there was another anomaly in the sources that really blew my mind. The freezer problem.
Ah, yes. This is one of the strongest arguments against the standard heat theory.
So if you take a radiometer and you stick it in a freezer, or just cool it down really fast, it spins backwards. The black side actually spins forward.
Right, into what would be the light. And the standard theory tries to explain this. It says, well, now the black side is radiating heat out faster, so it's cooler, so the process reverses.
That's the story. But the paper points out a huge issue with the physics here, at the molecular scale.
Exactly. When an object cools down, it radiates infrared light. And infrared waves are huge, about 750 nanometers or larger.
And an air molecule, nitrogen, say.
Tiny. An air molecule is about 0.3 nanometers.
So we have this massive slow wave in this tiny little particle.
It's like trying to move a tennis ball by making slow waves in a swimming pool. The air molecules are just too small to interact efficiently with those long infrared waves. They just shouldn't be feeling enough force to spin the vanes backward at the speeds we see.
Okay, so let's recap. Light pressure spins it the wrong way.
Check.
Thermal creep is too slow to explain the instant startup. And the cooling behavior just doesn't seem to match the physics of air molecules.
Huh.
We are zoo for 3 on the classic theories.
Which sets the stage perfectly for Lou's proposal, transimpact.
Transimpact. I have to say, it sounds like something from a sci-fi movie. What does it actually mean?
It stands for transition impact. And to understand it, we have to zoom in. Way in, past the vane, past the surface, down to the individual atoms on that black paint.
We're going quantum.
We are. The core idea relies on what happens when an electron absorbs energy. We all learn that when a photon hits an atom, an electron can jump to a higher energy orbital.
A quantum leap.
Right. But we usually just think of that as an energy change. We don't think about the physical shape, the geometry.
Okay.
The paper argues that when an electron jumps to a higher orbital, the effective size of the atom, the whole electron cloud, expands. And it's not a small expansion.
The source used nitrogen as an example, right?
Yeah.
What are the numbers?
Yeah. A nitrogen atom, in its ground state, has a radius of about 56 picometers. But when it gets excited, that radius jumps to 120 picometers.
So it more than doubles in width.
It's in radius. But think about what that does to volume.
Oh, that's cubed.
It's cubed. The paper calculates a volume increase of over 700%.
700%. That's not an expansion. That's an explosion.
At the atomic scale, yes, it is an explosion. And this is where the transimpact happens. I want you to visualize this.
Okay.
Imagine you are an atom on the surface of the vane, and standing right next to you, shoulder to shoulder, is an air molecule. It's a crowded space.
Wait, very tight.
Suddenly, in nanoseconds, you inflate a bubble suit that makes you 7 times bigger in volume.
I am violently shoving my neighbor away.
Violently. You aren't just taking up space. You are smacking that air molecule and sending it flying. That shove is the transimpact.
And because of Newton's third law.
Exactly. For every action, there is a reaction. You kick the air molecule away, so the atom on the vane get kicked backward.
And since this is a quantum jump,
it happens instantly. There's no warming up the skillet. The moment the photon hits, wham, the suit inflates, the neighbor gets kicked.
that explains the time zero acceleration. It's a mechanical kick, not a thermal process.
Precisely. It's a barrage of billions and billions of these tiny quantum kicks happening all at once.
So why does the black side move and not the white side? I mean, the white side has atoms too.
It does. But the white side is reflective. It's bouncing the photons away. The electrons there aren't absorbing the energy needed to make that jump.
They aren't inflating their bubble suits.
They're not. But the black side is absorbing everything. It's a machine designed for popping what the paper calls atomic popcorn.
I love that analogy. The black side is just constantly popping, kicking air molecules away, which in turn pushes the vane backward.
That's the theory. But, you know, a theory is just a good story until you can prove it.
And this paper details some experiments that are, well, they're pretty wild.
Yeah, especially the microwave one. But let's start with the flashlight test. This one was really clever.
So they took a focused beam of light and shone it only on the white side of the vane. Now, if the old heat theory were true, the white side would still warm up eventually, right? It absorbs some light. Sooner or later, the air should start pushing it.
It should. If it were just about heat accumulating, the white side should eventually start to retreat. But that is not what happened.
What did happen?
When they hit the white side with the light, the vane moved towards the light briefly. It sort of chased it and then stopped.
It just stopped, even with the light still on it.
Yes. which suggests that without the strong, efficient absorption you get on the black side, you just can't sustain the force. The reflection breaks the cycle. You don't get that continuous machine gun fire of transimpacts.
Okay, that is very compelling. But the experiment that really sold me was the microwave one. And I have to say, the paper explicitly warns that this destroyed their equipment.
Oh yeah, this is do not try this at home mad scientist territory. They needed a way to heat the veins really fast without using visible light.
Right, they wanted to see what happens when the object is just hot, but in the dark.
So they put the delicate glass radiometer into a microwave oven.
Wow.
They did. They blasted it for 6 seconds, just enough to heat the internal metal parts, but hopefully not enough to melt the whole thing. Then they cut the power.
Okay, so the lights are off, microwave is off, you just have a hot radiometer sitting in the dark.
And this is the smoking gun. It spins, but it doesn't just spin. It accelerates up to 7 revolutions per second.
7.
Yeah.
That's violent speed for a radiometer.
Yeah.
Usually they just drift.
It was humming. And the direction.
Cigarettes.
Backwards. The black side is suddenly driving forward.
Wait, okay, help me with this. The power is off, it's dark. Why is it moving at all, let alone that fast?
It's the cooling phase. Everything is hot and trying to radiate that heat away. Now, black surfaces are great at absorbing heat, but they're also great at radiating it away. The black side dumps its heat load almost instantly.
So the black side cools down way faster than the white side.
Yes. The electrons on the black side are dropping back down to their lower orbitals really quickly. The popcorn stops popping on that side.
But the white side is still hot.
The white side holds onto its heat a bit longer. It radiates more slowly. So for that brief window during that rapid cooling,
The white side has more atomic transitions, more of those bubble suit expansions than the black side.
exactly, the white side starts kicking the air.
And that pushes the white side backward, which means the black side has to move forward.
Correct. And because that radiative cooling happens so fast, the difference in force is extreme. That's what leads to that massive 7 revolutions per second speed. The old air pressure theory just has no way to account for that kind of sudden, violent reversal.
That is incredible. It really turns the device into a battle of quantum states rather than just a simple temperature gauge.
And there was one other experiment I wanted to mention because it addresses the shape of the veins.
The gold nanocrystals.
Yes. This was a separate study cited in the research. They coated a curved vein with gold nanocrystals. Now, usually, if you have a curved vein, like a little cup...
Aerodynamics says it should spin with the cup side trailing, like a parachute catching air.
Right, the open part catches the wind, but with these gold nanocrystals, it spun the opposite way.
What?
The concave side, the cup, was leading the rotation. It was cutting through the air.
That breaks basic aerodynamics.
It does, but transimpact explains it. The geometry of the nanocrystals and the curve itself focused the photon absorption in a way that the kicks were stronger on the convex side, which was powerful enough to override the air resistance.
It just shows that this atomic force can actually overpower what we think of as normal aerodynamics.
If the surface is engineered just right.
Yes. It's amazing how complex this toy actually is.
Yeah.
But we have to talk about the Goldilocks zone. The paper is very clear this only works at a specific pressure about 1 Pascal.
Right. Roughly the pressure of our atmosphere at 80 kilometers up, the mesosphere.
So why doesn't this work in my living room?
It's basically a traffic problem. If you have too much air, like in this room, it's a mosh pit. When your atom expands and kicks an air molecule, that air molecule immediately crashes into a billion others and just bounces back.
So the kick gets smothered.
It gets canceled out by the resistance. But if you have a perfect high vacuum, too little air, there's no one to kick.
Right.
You can inflate your bubble suit all you want, but if you're standing alone in the elevator, you don't push anyone. You generate no force.
So you need just enough air to get a good kick, but not so much that the air pushes back on itself.
Exactly. It's a very delicate balance.
So what does this all mean? I mean, solving the mystery of a 150-year-old toy is satisfying, but does transimpact actually matter outside of this little glass bulb?
This is the part that really makes you look at the world differently. If Lou is right, transimpact isn't just for light mills. It could be a fundamental mechanism of nature.
The paper mentioned Brownian motion.
Right. Brownian motion is that random jiggling you see when you look at dust motes or pollen grains in water under a microscope.
And we learned that it's just thermal motion molecules are warm, so they're bumping into each other randomly.
That's the textbook answer. But the source suggests that the random thermal vibration of water molecules alone isn't actually strong enough to push a whole pollen grain around as violently as we see.
But if you add transimpacts...
If you add billions of tiny explosive volume changes as electrons jump between orbitals in the water molecules, suddenly you have the force needed.
So the water isn't just vibrating, it's kicking.
It's kicking. It implies that temperature isn't just vibration, it's also this constant, explosive, popcorn-like expansion.
And what about phase transitions, like ice melting into water?
That's fascinating. Why does ice turn to water? We say heat breaks the molecular bonds, but how? Physically.
Right.
Transimpact theory suggests that as you add heat, the electrons get excited, the atoms expand explosively, and that physical expansion is what snaps the bonds holding the solid crystal together.
It literally shoves the molecules apart until the solid structure just collapses.
Yes. It redefines what we think of as heat. We tend to think of heat as shaking. This theory suggests heat is also shoving.
It really connects the quantum world of electron orbitals directly to the macro world of things spinning and melting.
That's the beauty of it. It takes this abstract concept of an electron orbital jump, something we draw on chalkboards as a probability cloud, and shows that it produces a tangible, physical force that you can see with your own eyes.
So next time you see a Crookes radiometer spinning away on a windowsill, you're not just looking at some quaint heat engine.
No, you are looking at a quantum machine. You are watching the visible result of electron clouds expanding and contracting, exploding like atomic popcorn billions of times every second.
And realizing that this little mystery that stumped Maxwell and Einstein might finally have an answer. It's a great reminder to always question the simple explanations.
Always. There's almost always another layer to peel back.
Well, thank you for diving deep with us today. This was a wild one.
My pleasure.
And to our listener, next time you feel the warmth of the sun, just remember, it's not just heat, it's impact. Catch you on the next deep dive.